Those of you just joining us, do your best effort at answering the 3 warm-up questions there. We'll go over it and we'll go from there. We're going to have more fun this morning than SL physics students on home quarantine should be allowed to have, really. So just keep that in mind. We might break some laws here.
Somebody says Newton's laws.
All right, I see Gus is in the house. Very good. Let's go about another 30 seconds. Again, if you haven't done so, do your best at trying to answer the warm-up question. I appreciate everyone muting their mic. Again, don't hesitate to put questions or comments in the chat box. And if you notice in the chat box, I've actually put a copy of these slides. Some of my HL students asked for this, and I suspect some of you would enjoy it too. So you can kind of follow along the deck at your own pace if for some reason I flip a slide too quickly and you wanted to jot down a few more things on the previous slide. So that's there. And in the future, if you don't see me post that and you would like to see it, let me know and I'll do my best. Okay, and I see we've gotten a few more people. Awesome. Cade, welcome, Cade. Okay, let's begin. Good morning, students. Welcome again. Today is April 28th. I so appreciate you getting up early to join us in our live session here. Today we're going to do some new content. That'll take, I'm guessing, 15-ish minutes. And then you're going to have time in breakout rooms to work on some concept builders. And I'll talk about that when we get there. First, let's go over the warm-up question and then a few announcements, and then we'll get into it. So here we go. The warm-up question, I think it's pretty self-explanatory. There's 1 and 2. 1 and 2 is basically just an identification of key wave vocabulary terms, both on a transverse wave up top there and on a longitudinal wave there at the bottom. And I don't feel like the need to basically elaborate much on these 2 warm-up questions. I'll just pause here for a few more seconds. Take a look. If you have any questions, feel free to put them in the chat box. If you don't have any questions, that's all right. While you're looking at that, I'll just go ahead and preview a slide I'm going to talk about here in a second. I do so appreciate those of you who participated last week in the IB Science Speaker Series. We had our 2 presenters, Alex Dare and Anshu Roy, and they were fabulous. They were great talks. And anyone who was there who wants to just kind of put a plug for them in the chat box, I would welcome that. I do want to make sure you know there are 2 more speakers coming up this week, and I'll present a slide here in a second with more information about them. Okay. David asks, why is the wavelength so long from compression to compression? I'm not quite sure I understand your question, David. On a longitudinal wave, the equivalent of a crest is that compression. So you just have to basically, if you were measuring it, so to speak, if I was taking a snapshot at the moment in time, which is what this is, I would just basically measure the distance from the center of one compression to the center of the next compression, and that would be one complete wave, one wavelength. Okay, if that doesn't answer your question, feel free to ask a follow-up question. Okay, and then number 3, Ella is at the ocean. She observed exactly 7 wave crests pass by. I should say her, I apologize. Okay, determine the wave frequency, wave period. Remember, frequency is revolutions or cycles or number of waves over unit time. So the 7 waves goes on top, the 42 seconds goes on the bottom. 742 is 1/6 of a wave per second, which is also the same thing as saying 1/6 hertz. Remember, frequency is often measured in hertz when it's waves per second, cycles per second, revolutions per second. The wave period, a couple ways to do it. The way I decided to do it is just invert that sort of relationship from A, because period is time per cycle. 42 seconds for 7 waves gives you 6 seconds per wave. You could have also said it's just 1 over the frequency, which would be 1 over 1/6, which would also be 6 seconds per wave. Okay. Let's talk about the Science Speaker Series. Then we're going to talk about some slides, talk about some new information, and then you will finish up with the concept builders in the breakout room. So as I mentioned, speakers last week were fabulous. We have 2 also amazing individuals this week. You can see on this Thursday at 1 p.m., Kristen Bott. She basically started in ecology and then became a data guru specialist. And I believe currently she works at Reed College or Lewis and Clark. I forgot which one it is, apologize. But she is going to be speaking this Thursday at 1 p.m. And then a person you may have heard on the radio, or maybe you've heard when your parents are listening on the radio, a woman named Jess Burns. She is a reporter, a science reporter for Oregon Public Broadcasting, and also an organization called EarthFix, which is affiliated with Oregon Public Broadcasting. So, and she's on this Friday at 11 a.m. Strongly encourage you to attend, even if you can't attend for the whole thing, attend for parts of it, because they have some wonderful things to say and just some wonderful words of wisdom too to offer. So it's a nice connection to the real world these days. Okay, so let's get into it. I'm gonna present a few slides here with some new information. You're gonna get some humor too, and then I'll get you into these breakout rooms that I've set up so that you can interact with each other in small groups. All right, so first thing I just want to establish is, so far in this unit, we've been talking about mechanical waves. And mechanical waves are waves that have to travel through matter, solid, liquid, gas, something like that. So things like sound waves, earthquake waves, waves on a rope, waves on a spring, those are all what we call mechanical waves. Just know at some point later in the unit, we are going to talk about electromagnetic waves. Electromagnetic waves are different in the sense that they don't need a medium to travel through. The most common example, the most visceral example we have for us of electromagnetic waves are those waves that we call light, basically in that part of the electromagnetic spectrum which our eyes can detect. So just keep in mind, sometimes it's important to make that distinction, and I'll try and do that as we head along here, mechanical versus electromagnetic. Okay, with that in mind, let's talk about something with mechanical waves. So notice we already talked about last week this idea of the distance from rest to crest is something we call the amplitude, right? So on this slide here, let's see if this works. And if I was to draw the amplitude here, I've got an amplitude here. I don't like that color. Let's pick a different color so it stands out. Here's the amplitude for this wave A, and here's the amplitude for this wave B. Well, a logical question you could ask is, how does the energy contained in wave A compared to the energy contained in wave B? And here's how it is. The energy of a wave is proportional to the square of the amplitude. So you could write an equation like this. Notice it's not an equal sign, it's a proportional sign. Energy is proportional to amplitude squared. And so, for example, in this scenario, if we said wave B has 3 times the amplitude of wave A, in other words, if the distance here were 3 times as significant, 3 times as long as the distance here, then how does the energy of wave B compare to wave A? Well, the amplitude, if you put in 3 times the amount there and you square that, you're going to get what? 9 times the amount of energy. So this is just an important, I don't know if it's super important, but it's just something I wanted to make you aware of, how there's this relationship between energy and amplitude of mechanical waves, and that's what it is. Okay, let's move on. This next slide's got some really good information on it. How do we figure out the speed of a wave? Well, certainly speed, we can always measure it the old-fashioned way, you know, change in position over change in time. But remember, in this case, this is a little different than, say, a baseball moving across the room, because the actual matter isn't moving translationally from one spot to another. It's kind of vibrating in place. So the speed at which a crest or compression, that's what we measure, the speed at which either a crest or compression is moving, and that's what we call the wave speed. Well, remember the time it takes for one crest to move, one complete wavelength, is the period. Let me say it again. For a crest to move a complete wavelength, that's going to be the period. So we know that if speed is displacement over time, then the wavelength is that displacement of that crest over that time period, which is the period. So you could write it this way, V equals lambda over T. I'm going to tell you that the more useful way to think about this is here on the left. We know that period and frequency are inversely related, right? So I can substitute 1 over frequency for the period. And if I do, the wave speed equation looks like this, that the speed of a wave is equal to the wavelength of the wave measured in meters, usually meters, doesn't have to be, and the frequency measured in hertz. And this would be the wave speed. If you're still keeping an equation sheet, which hopefully you are, I would definitely add this to the equation sheet. I will make a mental note here to try and put out an updated equation sheet sometime in the next few days. If I forget for some reason you really need it, please send me a message and that'll jog my memory. Okay, so let's use this wave speed equation in a sample problem here in the next slide. So let's say Abby has a slinky and she moves her hand so that 6 compressions pass a given point in 12 seconds. The distance between the compressions is on average 40 centimeters. A, determine the frequency. B, determine the wave speed in meters per second. All right, so how are we going to approach this? Well, here we go. So let's figure out our givens. Let's see, 6 compressions. Okay, so we have 6 waves. And the time is 12 seconds. And we know that the distance between the compressions is on average 40 centimeters. Well, the distance between compressions, that looks like that's the wavelength, right? So lambda equals 40 centimeters. So we know 6 waves in 12 seconds and a wavelength of 40 centimeters. So how are we going to figure out the frequency? Well, we know frequency is waves or cycles per time, right? So if we have 6 waves in 12 seconds, that gives us a frequency of, I'm just going to use the decimal, 0.5 waves per second, or 0.5 hertz. Okay, with that in mind, we go to B, the wave speed. Wave speed, as we recall from the previous slide, is frequency times wavelength. So now what we can do is we can use our answer from A, 0.5 hertz, multiply it by the wavelength. I could keep the wavelength in centimeters if I wanted to. My answer would be in centimeters per second, though, then I have to convert my answer. So I'm going to actually convert right now. And remember, dusting the cobwebs off, 40 centimeters, we have 100 centimeters is 1 meter, right? Little factor label review here. So 40 divided by 100, that's 0.40 meters. All right, so if you take half of 0.4, that's going to be what? 0.2, right? So our answer becomes 0.20 meters per second, or 20 centimeters per second. And there you go. Okay, so we know wave speed equation. This is going to be a super handy equation from here on out. And I will tell you, it even becomes handy when we talk about electromagnetic waves, because this wave speed, when we start talking about electromagnetic waves, becomes another constant, which we call the speed of light. It gets the symbol c, lowercase c, and it's got the speed of light in a vacuum has a constant quantity. Okay, so let's go to the next slide. No. Okay, we're going to talk about a few more things here. We're going to talk about wave reflection and wave superposition. So wave reflection is something we intuitively know, but let's just make sure we understand what happens here. If you look at these wave fronts coming in here to that reflective surface on the right, what's going to happen when these wave fronts, again, you're looking at the wave from top, like a bird's eye view. Well, we know that a certain portion of those waves are going to bounce off, and you can see it happening there in that little sort of animation. And so as it bounces off, it obviously changes direction and continues to travel in a very predictable path, by the way. Notice this can happen like when waves are coming in flat, or it can also happen when they're coming in from the side. Okay, so flat wave fronts, spherical wave fronts, you get this sort of reflection. Okay, that's just kind of something common sense because we see it a lot throughout our life, but it's important to just name it. So that's what we call wave reflection. When a wave hits a boundary and a part of it bounces off, so to speak, changes direction. That's going to be an important building block when we start talking about physics of sound, which will be next week, and music. Okay, so with that in mind, one thing to keep in mind is when that wave bounces off, neither the frequency nor the wavelength changes. It keeps the same wavelength, keeps the same frequency. That's not going to be the case when we talk about something called refraction, which we will talk about probably next week as well. Okay, you guys ready for the joke? Oh, hold on. I got to get prepped here. I forgot to do this ahead of time. Hold on. You know what they say? Anything that's worthwhile is worth waiting for. So give me a moment here. All right, here we go. So here's the joke. How do you make a holy water? Oh, gosh, totally messed this up. I'll just ask you, how do you make holy water? You boil the hell out of it. All right, awesome. All right, let's keep going because I want to talk about a super cool phenomenon that is so important that waves display. Okay, and so just take a look at what's going on here in this animation. By the way, again, I think I mentioned this before. This gentleman, Dan Russell, is like an acoustics god. And if you're ever interested in going deeper and deeper into stuff, he's got these amazing websites with these amazing simulations like this one. So notice what I have here is I have two waves traveling in opposite directions, and they come together. You notice the red wave on the left and the blue or purple wave on the right. They come together in the middle there. My question to you is, what happens to that wave, the two waves, when they meet? Clearly something is going on there. And hopefully you notice that for that split second, it seems like the waves combine, right? They seem to add up. The rope gets has a bigger displacement. And then after that point, it looks like they just keep moving along in their original path, right? Because the red and the blue, they just keep moving after they combine for that moment. So the key idea here is something called wave superposition, also known as wave interference. And it's simply the addition of two or more waves passing simultaneously through a medium. So if two or more waves meet at the same point in some matter, they are going to interfere with each other in some way. The two extreme cases of this are things we call constructive interference and destructive interference. Constructive is one extreme, destructive is the other, and we're going to talk about both. Notice that wave interference can be either just completely constructive, completely destructive, or it can be a mix of the two. So let's first consider this scenario here below, where I have, notice the two wave pulses there, the red and the blue. Let me just show you that one more time, just in case you missed it. All right, so notice what happened there. If we kind of deconstruct it, if I measure carefully the amplitude of the red wave and the amplitude of the blue wave, and if I was able to carefully measure the amplitude of the resulting wave when they come together, notice what I have here is these two pulses are what we call in phase. You can also think of it as crest meeting crest, and I'll probably say that a lot. Crest meets crest in constructive interference, or compression meets compression. If either of those cases happen, then you get constructive interference, meaning the resulting wave is bigger. It has a larger amplitude. In this case, it would have exactly twice the amplitude for that split second of either individual wave, because it's a simple addition of the amplitude of one wave with the amplitude of the other wave. Okay, so that's what we call constructive interference. When crest meets crest, trough meets trough, two waves that are in phase with each other. What do you think we're going to talk about in the next slide? Yeah, you guessed it. We're going to talk about destructive interference. Okay, so let's go there. Destructive interference. What's happening there? If I look at two wave pulses that are out of sync with each other, 180 degrees out of sync, notice in this case, the red is on top, blue is on bottom. It's like crest is meeting trough. Okay, what happens when they come together? The amplitudes, in this case, because they're exactly the same amplitude but in opposite directions, they cancel each other out. And so this is an example of the most extreme example of destructive interference, when you get a crest meeting a trough and you get a cancellation of any sort of wave action for that split second, okay, when the waves meet. So I'll give you a second here to just kind of jot down a few more notes if you want to about this. And I just want to tell you that these are really important principles, and we're going to build on them, because what we're going to be doing in the coming sessions, actually probably next session, is we're going to look at particular special cases of constructive and destructive interference where things called standing waves are set up. And standing waves are pivotal to understanding the physics of music, physics of musical instruments. And we're going to spend some time on that next week. Okay. All right. So let's talk about one more thing. This last thing is not something that you will be tested on at all, but I just think it's super incredibly awesome and useful and appears a lot. So you'll see this word used, Fourier Transform. And I just want you to have a sense, a little bit of a sense of what people are talking about when they talk about a Fourier Transform. So you can look smart and be smart. Well, you already are smart, but you can even look smarter and more importantly, understand what they're talking about. So, and a Fourier transform or a Fourier series is really just using this principle of wave superposition. So let's take a look at this scenario here. Let's say I have a certain wave that looks like this. And if you recall, maybe you haven't done this in math, or maybe it's been a while, but you can characterize that with a certain certain sinusoidal function there, okay? And then notice if I have a different wave here with a slightly different sinusoidal function, right? It's not in phase, it's not out of phase, it's kind of offset in some way. Then I've got another wave here, okay? And it's got its own sort of amplitude, its own sort of period, wavelength, etc. I've got a fourth one here, okay? And finally, I've got a fifth one here, okay? Now, the principle of superposition still works. If all these waves come together in the same medium, then what I need to do to figure out the resulting wave is I just need to add the amplitudes, the crests and troughs of all these waves to get the resulting wave. And in this case, it would look something like this big fat green line. This is what we call a Fourier transform, and it works both ways. So I can take individual sinusoidal waves or cosine waves, add them together in different amounts, so to speak, to create a more complex wave, the one you see in green here. The more, not more powerful, but equally powerful, if I am given a complex wave like this green wave, if I'm given that, then I can work in reverse and I can say, oh, this complex wave actually is the summation of these 5 different waves with this sort of frequency and this sort of amplitude on each of the waves. And that is incredibly powerful in the world of science. I just can't tell you how powerful that is. And also, if you think about it in terms of musical instruments, the kind of waves musical instruments create are most often these green complex waves, but they really are just a summation of usually just a few simpler wave patterns. And so you can take the complexity of a situation and you can distill it into a couple of simpler patterns. Fabulous stuff. Okay. So yeah, and in this case, this kind of looks like what we call a sawtooth wave, meaning it will kind of go up linearly and then drop down really quickly, and then go up linearly and drop down really quickly. So that's just something for you to know. Okay, this last part of today, the remaining, I would say this is going to be anywhere between 15 and 20 minutes, depending on how much, 25 minutes you could say. I'm going to be assigning you, I have assigned you into breakout rooms. But these breakout rooms are individual Google Meet sessions. I've already set them up. And when I post the link to the document, you're going to see your name and there's going to be a link for the breakout room. So you're going to go into that breakout room, and there's going to be anywhere from 2 to maybe 4 other people in that room. One thing I do want you to note before you go into a breakout room is notice the people that are in on this call. If you're the only one from your table in on this call, then feel free to join any other breakout room that you want to join, because I don't want you to be in a breakout room by yourself. That kind of defeats the purpose. So take a look, join any other breakout room that you feel comfortable joining. What are you going to do in the breakout rooms? Well, there are these wave concept builder games, and I've put the link to those games on the blog. We've done this before. These are on physicsclassroom.com. And so there's a series of games there that I want you to play, and I first want you to play them together as a group. So in other words, here's what you're going to need to do. You're going to need to have one person. Well, first of all, that's what you're going to do. And if you finish that and you have time, you're going to start problem set 7-1. Problem set 7-1 went live on Google Classroom, or will go live on Google Classroom in about 15 minutes here. And that's going to be due next Sunday, on Sunday night. Okay, it's a problem set. I think it's got 12 problems in it. So those are the two things you're going to do. Wave concept builder games, start problem set 7-1. But let me just talk about the wave concept builder activities. So I want you to get more experience applying these concepts and equations we've been talking about the last 2 weeks. You've done these games before. What I want you to do in these breakout rooms is just decide on one person to share their screen. This obviously needs to be a person who can actually bring up the physics concept builder games on their screen. So a smartphone probably won't work so well, but a better thing would be like a tablet or a computer. And then I'd like you to work through like the first couple of scenarios as a group. So don't just have the one person do it, just have a conversation about what the problem is asking, what you think the answer is, how do you apply the principles we've been using. So group conversation is key. Also feel free to visit with each other socially a little bit if you feel like you want to or need to. Check in with each other, see how each of you is doing. Okay, totally expected, totally good with that. And so work through at least the first couple as a group. Don't just guess and check, okay? I know sometimes students just like to guess and check, but try and work through them on paper with pencil, applying the sort of concepts we've been talking about. I am going to be visiting each of the rooms. The way I've set this up, I can't actually speak, but I can offer feedback or support through the chat. So if you have a question for me, put it in the chat, and when I get to your room, I'll see that you have a question, and I will do my best to answer it in the chat function. Okay? So you can certainly reach out to me via the chat function. All right. Yeah, so in a moment here, I'm going to put that link to that document up. And so again, your task is to go to that designated breakout room, go to the blog and read the instructions and go to the links. Again, don't just guess and check. Try and figure out some logical steps. Have that group conversation. Complete about 2 to 3 problems on each activity. I expect the total time to be spent somewhere between 15 and 25 minutes, up to you. When you feel like you've had your fill, certainly you can just sign off on the call. We're not going to come back to the bigger group. So that's going to be the concluding activity for today. And also what I wanted to say is after you do the first 2 or 3 problems together with one person sharing their screen, if you have the ability to, I would recommend you then go and continue doing it individually while staying in the group Google Meet. And if one of you then has a problem with what they're seeing, like, hey, I can't get this answer right, can you guys help me? They can present their screen, so you can help each other that way. Okay. Let me just see, are there any questions? If you do have a question about what I've been saying, feel free to post it on the chat. And while you're doing that, I'm going to go get the link for the breakout rooms and post it on there. Okay, I don't see any questions. I'm going to stick around here in the main meeting for a few minutes. So if you do have questions, feel free to hang out. And actually, Michael, if you're still on the call, I would love to just talk to you for a quick moment before you go to your breakout room. So Michael Habib, if you can stay on this call for a second, that would be great. The breakout room link is there. Again, at this point, this concludes this call. Feel free to hang up this call if you need to in order to transition to your breakout room. Thanks, everyone. I'll see you over there.